Hi there, and welcome to today's class. For today's class, we'll be talking about the elastic properties of solids. We'll be looking at key concepts like elasticity, Young's modulus, Hooke's law, and etc. But before then, let's look at some of the key concepts in discussing the elastic properties of solids. In this topic here, there's a key term known as elasticity, right? Something called elasticity. All right, this is like one of the key terms in discussing the elastic properties of solid. Now, definition, what exactly is elasticity? By definition, elasticity is simply the ability of a solid to regain its original shape and size after it has been distorted by a force. Okay? The ability of a solid to regain its original shape and size after it has been distorted by a force is called elasticity. When we say the word distorted, what does distort? To distort, what does it mean? To distort simply means to change the original shape or size of an object. That's the meaning of the word distort. So when you distort a solid object, for instance, you're simply changing the shape or the size of that solid. It's either you're increasing the shape or size of the solid or you're reducing it. All right. So when you increase the length or reduce the length of a particular solid, we can say you distorted that solid. That's not the word distort. So from this now we can now say that, of course, one thing to notice this, not all solids are elastic. Some solids are elastic and some solids are not elastic. All right. Solids that are elastic, or we can say elastic solids, are simply solids that can regain their original shape and size after they have been distorted. All right. So solid that can undergo elasticity or solid that has elastic properties are said to be elastic solids. Example include plastic. All right. If I draw a plastic solid, most likely to compress there. Also, we have spring. All right. If I pull a spring, of course, most likely it will come back. That's if it has not exceeded the elastic limit, which we'll discuss much more later. All right. So spring plastics are said to have elastic properties. Now we also have solids that do not have elastic properties. Kind of, you don't really have elastic properties. Examples, you have wood. Right. Wood is not really elastic. Okay. You have things like glass. Right. Glass is not very elastic. Right. So these are like some of the examples of elastic and non-elastic solids. All right. So when it comes to the concept of elasticity or elastic properties of solid, there's a law there that is very key. That law is known as Hooke's law. So we cannot discuss the concept of elasticity without talking about the law known as Hooke's law. All right, so Hooke's law was propounded by a scientist called Robert Hooke. Hooke's law says that provided the elastic limit of a material has not been exceeded, then the extension produced in any elastic material is directly proportional to the force causing it. All right, so that's Hooke's law, right? States that supposing that the elastic limit of a material has not been exceeded, then the extension produced in an elastic material is directly proportional to the force causing the extension. Now, I'll explain this briefly using a diagram. Let's say I have an elastic material, let's say a spring, all right? Let's say I have a spring. So let me say I have my first point, A here. So A, I have this one here. And I have a spring, something of this nature. All right. So I have a spring here, and I'm saying from this point to this point, I'll call this L. This is L, where L means length of the spring. That's L. L is length of the spring. I have this. All right. Let's say I now attach a particular mass. So let me have a second one here. Um, We are saying this is the same height. This height and this, they are the same thing. So I have B here. Let's say I attach a mass here. I attach a mass or a weight here. If you attach a weight or a mass here, what do you expect? You expect that the spring will move downwards, right? So the spring will sag down a bit. Now, this shows what is called distortion. The sagging of the spring here is because a load or a mass or a weight has been applied to the spring. So to now move downwards, I'll have something that looks like this. I'm having this, this. Okay. So I have this because I attach a particular mass. Let me call this mass M1. All right. So I attach a particular mass M1. The original length of this spring was from this point here to this point. So this was the original length. This is L, which was the original length of this spring. Then observe that when I attach a mass M1, the length increases by this small amount. So this small amount we will call an extension. So I'll call this E1. E1 means the extension when I applied mass 1. That's E1. I'll call this. So this additional length that is caused by the application of this mass is called E1 or is called an extension. That's called an extension. Okay, so what happens if I apply a bigger mass? Now this is mass M1. What if I use a bigger mass, say mass M2? What happens? If I apply a bigger mass to this, it will sag further downwards. So the idea is this: the greater the mass I apply to this, the further it sags downwards. So perhaps I'll have, let's say, something like C. Let me draw a third diagram. So this height, they are the same thing here. Let me draw a diagram C here. And let's say I apply mass M2, where mass M2 is bigger than mass M1. What will happen? I will have that this spring will sag further downwards. Okay. Apply this. Okay. Let me draw it to be bigger, just to show that M2 is bigger than M1. So I'll call this M2. All right, so what do you observe? You observe that when I applied a bigger mass M2, it sagged further downwards. Don't forget that the initial length, which was L1, or L from here, was still the same path. Let's say here as L. We are saying this length is same thing as this, same thing as this. So here as your L, I'm having L from here to here, which is the initial length of the spring. Also, I now have this one here. Let's call this is M2. Let's call this E2. So I have this. So the idea here is that the more I apply a bigger mass, the more the extension. See that E2 is bigger than what? E1. So the more the mass, or the greater the mass, or the greater the weight you apply to the spring, the more the extension. That's why we can say E2. I can say E2 is greater than E1. All right. So the more the mass, the bigger the extension. So this is what Hooke's law is trying to say, that the extension produced in an elastic material, example a spring, is directly proportional to what there, the force or the weight applied, which in this case I'm using just a mass, right? So you can say weight if you want to, all right, provided that the elastic limit of the material has not been exceeded. So this is basically what Hooke's law is saying. Now, in the mathematical form, mathematically, we are saying that the extension produced in an elastic material is directly proportional to the applied force. So in a mathematical sense, force is directly proportional to extension. So I have this. So let me call force F directly proportional to, let me call extension E. Okay. So I'm saying for this, you can choose to use mass, that's M, or you can use weight, W, or force, or load, right? They have different names, but you get the concept. The heavier it is, the more it sucks. All right, so here's a question. The question is this. If I look at Hooke's law critically, Hooke's law states that the extension produced in an elastic material is directly proportional to the force. So from Hooke's law, we have that it is extension being directly proportional to force. Now let me explain that. From Hooke's law, I'm saying this, that if I should take Hooke's law word by word, I should be having that extension is directly proportional to force. This is what I should have as my mathematical expression because we had extension in that statement before force. Now, how come in my mathematical expression, I'm seeing force before extension? Why is it so? And the answer is very simple. The answer is this. If I look at diagram ABC, before an extension was produced, a particular mass or a particular weight or a particular load or a particular force was applied. So in Newton's law, or in Hooke's law, okay, so in Hooke's law, he mentioned extension before force. Yes, that's okay. But in a real sense, there can be no extension without force. So a force or a weight or a mass must first be applied before there can be an extension. And that's why when it comes to mathematical form, we put the force first before the extension. So that's why we have this one here, correct, and not this. Well, technically they mean the same thing though. All right, let's proceed. So this now becomes a mathematical statement. And we said in mathematics, if I have a proportionality sign, what do I do there? I will take this man off, I'll put an equal to, and I'll introduce a constant. So it means that F changes to equal to, put your constant, then put E. So I have this. All right, so I have this. Where K is a constant of elasticity known as the stiffness of spring, also called spring constant. It's also called force constant or spring constant. All right, so know that the term K has three names. You call it a force constant, you call it a spring constant, you call it a stiffness of spring. They are all the same thing. From here, if I make K to be subject of the formula, we have that F is equal to KE. To make K stand alone, we'll divide both sides by what attached to K, which means divide here by E, divide here by E. This cancels this. So you can say F is equal to K over E. All right, so from here we can say that K, stiffness of spring, is equal to F all over E. Let's look at SI units. So if I look at the SI unit, force is measured in Newton, extension is in meters. So you can say SI unit is Newton per meter, this, or Nm to the power minus 1 in index form. So the SI unit of stiffness of spring is Newton per meter. We'll just take a few examples on this and then we would proceed. All right? Take a few examples on this and then we can proceed with this topic. All right, so let's take a first example. This one says a force of 0.8 Newton stretches an elastic spring by 2 centimeters. Find the elastic constant of the spring. All right, let's get this solved. Solution. As usual, my first task is to list out given parameters. The first thing I'm giving here, they said a force of 0.8 Newton. The first thing I'm giving there is force F is equal to 0.8 Newton. Number 2, they said stretches an elastic material by, stretches an elastic spring by 2 cm. That means the extension is actually 2 cm. We are asked to find the elastic um, constant of the spring. So this should be very easy. We said elastic constant K is equal to force over extension. Now it depends on your options. If your options are in Newton per centimeter, that's Newton per cm, you don't have to convert. But in this case here, my options are in Newton per meter. That means I have to convert the extension to meter. All right. So how do I convert 2 cm to meters? To convert 2 cm to meters, we'll have to divide 2 cm by 100. So it becomes 2 all over 100, and that gives me 0.02 in meters. Okay, let me write that one outside. So let me write it out. So it becomes that's equal to 2 divided by 100, and that should give you about 0.02 meters. All right, so this is the value of the extension in meters. We have to find the elastic constant. Recall the elastic constant K is equal to force all over extension, and that's equal to the force is 0.8 all over. The extension is this one here in cm, which is 0.02. All right, if I punch this 0.8 all over 0.02, that gives about 40 in Newton per meter. So I have this. So hence, the answer to this question is 40 Newton per meter. Let's take another example. All right, so let's consider this next example. This question says a force of 2 Newton stretches an elastic material by 30 millimeters. What additional force will stretch the material 35 millimeters? Assume that the elastic limit is not exceeded. All right, let's get this done. Solution here. As usual again, first task, list out given parameters. Now the question here says a force of 2 Newton. So I'm given a force, number one, I'm given a force F as equal to 2 Newton, okay? They said stretches an elastic material by 30 millimeters. So number two, I have the extension E as equal to 30 millimeters. Okay, what additional force? So I'm looking for another force. So if I'm looking for an extra force, perhaps let me call the extra force, let's say F2 per se. Let's call the second force the F2. Okay, let's call the force the F2. If this is F2, let's now rename this as F1. Now, since F1 stretches the elastic material by this, let me call this E1, where E1 is simply the extension of F1. So I'm having this. They said what additional force will stretch the material. So they're saying what force, that's F2, will stretch the material by, so I have a second extension as 35 millimeters. What additional force will stretch the material by 35 millimeters? So what do we do here? How do we get an additional force? Please, they're asking for an additional force. How do you get additional force? Now, if I let's say I have let's say I have a force of 5 Newton. Let me call this F1, and then let's say I have another force F2 as being equal to 7 Newton, right? F1 is 5 Newton, F2 is 7 Newton. Now, question is this. If I should ask you what force has been added to F1 to get F2, you will say that for this case here, the added force would be 2 Newton because 5 plus 2 gives you 7. In other words, the additional force is simply the difference between F2 and F1. 7 minus 5 gives you 2. That's how we get the additional force. So in this case here, for us to get the additional force, we have to subtract the value of F1 from F2. That's how to get the additional force. Now, how do you do that? We can't subtract F1 from F2 if we do not have the value of F2. So our first task will be to find the value of what? F2. How do we find the value of F2? The first thing is that we use the concept of Hooke's law, the mathematical expression of Hooke's law, to find the value of k first. All right, so let's get k. Let's recall something. Recall that f is equal to ke. Now, since I have F1, E1, I'll just say F1 and E1. So I can say F1 is equal to KE1. Now, you may want to ask, why is it that K does not have 1? Why didn't I write F1 equal to K1 E1? And the answer is simple. I did not put F1 equal to K1 E1 because K is a constant. That's why it's called a spring constant. So it does not change. For any material, for any spring, the K is always constant, regardless of the additional force or the extension. K is constant. So there's nothing like a K1, K2. K is K. In other words, to get K here, I'll divide here by E1, divide here by E1. This cancels this. So I can say the spring constant is equal to F1 all over E1. So what's F1? F1 is 2 Newton. So 2 Newton all over. E1 here is in millimeters. Let's try to convert. Anyways, let's try to convert. Convert E1 from 30 millimeters to meters. I'll divide by 1000. Please, that's how you convert from millimeters to meters. If I divide this by 1000, I should have 0.003 meters. So if I should divide, I have 0.03 meters. Yeah, I'll have 0.0 meters. Also convert this one here to meters, becomes 35 all over, divide by 1000, and that will be equal to, divide this by 1000, you have 0.035. Yeah, I'll have 0.035 as my answer, of course, in meters. All right, so I've done this. So E1 in meters is simply 0.03 in meters. So let's do 2 divided by 0.03. That's about, so that means K is equal to 66.67 approximately in Newton per meter. That's the value of K. All right, so let's use this value of K to find F2. Also, we know that F or F2 in this case is equal to, just like you have here, K E2. Don't forget we said K does not change. It's a constant. So from here we can have that F2. So F2 is equal to K. K is 66.67 into E2. E2 is this value in meters, which is 0.035. All right. If I multiply this, so 6.66.67 multiplied by 0.035, that's about 2 points in two decimal places, 33 Newton, because I'm calculating for force, F2, and force is in Newton. So I'll put my units. So they're asking you what additional force. So from here, therefore, we can say that additional force is equal to, we said, is difference between F1 and F2. So it becomes F2 minus F1, which is 2.33 approximately, minus F1 is 2, that's 2, and that will give you about 0.33 Newton. So this is the value of the additional force. This is how we solve this question. So if you like this video, simply hit the like button and subscribe to this channel. Also, you can check out my other classes on physics, mathematics, chemistry. I have over 100 classes on physics, mathematics, chemistry on my website. Simply visit www.journalimoney.com/courses and you see the JAMB/WAEC classes. So you can create an account with the website and then order for the course and to give you a lifetime access to all of these courses. So if you like this video, simply hit the like button and subscribe to this channel. So in the next class, we'll talk about the concept of stress, strain, Young's modulus, elastic potential energy, and work done in a spring.